All right, great. Good afternoon, and welcome to this afternoon's session on graph computing, where we have 3 great talks for you. And the first one up is from Zhijia Zhao from UC Riverside to tell us about Glign.
Thank you, Chris. Can you hear me well? Okay, cool. So this is a joint work with my colleague Rajiv Gupta and our co-advisor student Xizhe. First, let me start with a little bit of background. In the last 10 years or so, people have designed a lot of graph systems, and the majority of them process a single query each time. And here the queries are the ones that need to access the graph iteration by iteration until the evaluation reaches a predefined threshold or a fixed point. Examples include BFS, sorted path, connected components, and etc. More recently, people have proposed graph systems that are able to process multiple queries concurrently. So basically, a batch of queries are evaluated together on the same graph. Such queries are usually vertex-specific, such as a single source sorted path, which calculates the sorted distances from a particular source vertex to all the other vertices in the graph, so that people can ask different queries regarding different source vertices. The intuition behind this design is that these different queries need to access the same underlying graph, so evaluating them together can help us to share these graph accesses. For example, the edges loaded by one query may be also accessed by another query. So overall, the data locality can be improved. Interestingly, we found that this is not necessarily the case. So this figure shows the last level cache misses of evaluating 64 concurrent queries. And we compared a state-of-the-art concurrent graph system called Creo with the sequential evaluation using Ligra. And from the data you can see here, the reduction of the last level cache misses could be relatively limited. And in some cases, actually, the misses can be increased during the concurrent evaluation. So why does this happen? In the following, I'm going to use an example to illustrate what's happening behind the scenes. So here, assume that the graph system is evaluating 2 SSP queries concurrently. And one starts from the source vertex V8. The other starts from the source vertex V2. The red table here shows the vertices that are activated in each iteration, which are also known as the frontiers. So from this example, you can see that even though the evaluation of both queries need to access the same set of vertices, they access them in different iterations. So the amount of sharing between the 2 queries is limited. However, if I change the scheduling a little bit, let's say we delay the evaluation of the second query by 2 iterations. Now you can see the ratio of shared accesses between the 2 evaluations got increased a lot. So here we say that the alignments between the 2 queries are improved. So in fact, we not only find this misalignment across different queries, but also within the same query, because the vertices can still be accessed at different time within a single iteration. Moreover, when we consider putting different queries into the evaluation batch, maybe one query have a better alignment with some of the queries than the other queries. In this example, you can see that the 2 SSP queries from V1 and V2 are better aligned because they have more shared graph accesses. So that is about the cross-query alignment. So the goal of this work is to systematically align the graph accesses at the different levels of the concurrent query evaluation. In the following, I will introduce the basic ideas of our techniques for each level of alignment. Let me start with the intra-iteration alignment. So an intuitive design to evaluate the concurrent queries together is to maintain a separate frontier for each query. However, this does not guarantee the same vertex will be accessed at the same time for all the queries. So to address this, our solution is to propose a single frontier for all the queries in the evaluation batch. So in this way, when one vertex is evaluated, it is evaluated for all the queries in the batch. So in this way, we can guarantee that the access, we can have a single access for all the queries in the batch. However, you may have some concerns with this design because here, for the vertices that are not activated by all the queries, you may have to do some extra evaluations. So the first question you may have is that, is this correct? So we have proved that as long as the vertex function that we use to evaluate each query is monotonic, then we can guarantee that these extra evaluations won't change the final results. And fortunately, that already covers a group of commonly used graph problems. Second, how about efficiency? So here, actually, we are exploring a trade-off between computations and the data locality. With a single frontier, we may perform some extra evaluations on some of the vertices. But on the other hand, we have better aligned graph accesses. And also, we reduced the memory footprint because we don't have to maintain the separate frontiers. And based on our evaluation, we found that the benefits clearly outweigh the costs. So overall, we found a good amount of speedups. So that is the intra-iteration alignment. Next, let's talk about the inter-iteration alignment. As I showed earlier, aligning these different queries, the iterations of different queries may help to improve the sharing of graph accesses. However, the question is, what is the proper alignment, right? For example, if we want to delay the evaluation of one of the queries, how many iterations should it be delayed? Here, our key insight is that we should align the heavy iterations during the graph evaluation. So these are the iterations that actually dominate the overall graph accesses during the whole evaluation. If these heavy iterations are aligned, then it is more likely to find shared graph accesses within the same iteration. So the question becomes, how do we identify the heavy iterations? And here we use a simple heuristic. That is, as long as the evaluation reaches a high degree vertex, we say it has reached the heavy iterations. However, we cannot check this at the runtime if we use the query oblivious frontier, because in this case, we cannot tell the vertex that is activated by which query. So to address this problem, we propose an offline approach. That is, we profile the least hops from each vertex to the closest high-degree vertex. And this can be done easily with a BFS query on the high-degree vertex. So in this example, we can find that it takes at least two hops from VQ to reach the closest high-degree vertex, and it takes at least 9 hops for VP to reach the closest high-degree vertex. So correspondingly, for the two queries, we will delay the query starting from VQ by 7 iterations. In this way, their heavy iterations would be better aligned. Next, I will briefly talk about the cross-query alignment. Actually, this one shares the same heuristic as the inter-iteration alignment. So for a given buffer of queries, we define a batching window, and then we rank the queries within the window based on the heuristic. That is, the least hops from the source vertex to the closest high-degree vertex. And then we generated the batches based on the ranking. In this way, the queries in the same batch would be better aligned in terms of the heavy iterations. We implemented the above ideas as a runtime system on top of the Ligra framework, which is a popular in-memory graph processing framework. And we call our system Glign, and it integrates all these three techniques that I mentioned earlier. We evaluated the Glign using the commonly used graph queries that are randomly generated and are grouped based on their types. So we cover both the homogeneous queries and also heterogeneous queries. And we use this commonly used graph to evaluate our system. And we run it on a 30-core machine with 512 gigabytes of memory. This figure shows the speed up of Glign and also a couple of other state-of-the-art systems. The baseline here is the sequential evaluation using Ligra. By sequential, I mean it evaluates the queries one by one. But for each query, it is still evaluated in parallel using all the CPU cores. And from here, we can see that our system can outperform the state-of-the-art system Creo by about 2.5 times. And looking deeper, we found that the benefits mainly come from the improved data locality. And here, the figure shows the last level cache misses reduction. The baseline, again, is the sequential evaluation using Ligra. And we can see Glign can substantially reduce the amount of cache misses and up to 90% comparing to Creo. So to conclude, in this work, we observed an interesting performance issue in concurrent graph evaluation, that is the misalignment between the graph traversals. And to address that, we proposed multiple alignment techniques targeting different levels of the concurrent query evaluation system. And finally, we implement our system as a runtime system, and we show that it can outperform the state-of-the-art solutions substantially. So that's my talk. Thank you for listening. Any questions?